Alright guys, we're back here in 14.2 talking about properties of parallelograms. We've dealt with parallelograms already, especially in our lesson dealing with parallel lines with a single transversal. So now essentially we have two parallel pairs that create a quadrilateral. So our essential understanding here is parallelograms, their opposite sides must be parallel and do not share a vertex, and opposite angles do not share a side. Now why does that matter? Because in a parallelogram, opposite angles are actually congruent to each other, and we will look at that proof here in just a little bit. We can abbreviate parallelogram by using this little symbol that looks like a parallelogram, and multiple parallelograms, you just throw a little s inside of there. So our first theorem involving parallelograms is Theorem 40. It states that in a parallelogram, my opposite sides are congruent. So AB would be congruent to CD, and likewise BC is congruent to AD. So our proof for Theorem 40 here, the only thing given to us is that ABCD is a parallelogram. So based off that, we need to prove my congruent opposite sides. So since it's a parallelogram, we start by knowing that AB is parallel to CD and likewise BC parallel to DA. That's just definition of parallelogram. Then angles 1 is congruent to angle 4 and angle 3 is congruent to angle 2 because if lines are parallel, we have alternate interior angles. If that's hard to see for you, give me a moment. So a little bit more vocabulary for you here. Consecutive angles are angles which share a side. So the first angles they give you the example of is A and B. They share this side here, but if I look at A and C, they do not share a side, so they're not consecutive. But if I look at B and C, they are consecutive because they share a side. So as long as they share a side, we have consecutive angles. So now we talk about Theorem 41, which is why we care about consecutive angles. So what we see is that consecutive angles are always going to be supplementary. Now why that is because in a parallelogram, we know that BC and AD are parallel. So if I were to slide this, it didn't group everything. In just a second to make sure this all groups. So if I were to slide this up, well, it still didn't group everything, but if I slide this all up, and look at where angle D was, it's now supplementary with angle C up here because it will make a straight angle when I combine the both of them. I can do that in any of these situations and see that the angle pairs must be supplementary. My highlighting is getting a little quirky. So that's the big thing to remember. And also what that tells me then is since pairs of consecutive angles equal 180, then opposite angles are congruent because if I look at, and I'm probably jumping ahead, I know this is another theorem that we're going to look at. If A and B equal 180 and B and C equal 180, then A and C must be equal to each other. Now you don't have the picture of this in your notes, but you did have problem 1 that you just looked at, so hopefully you solved through that problem. And now we're here at problem in the got it that relates back to problem 1. So it says if we change the measure of angle S to be 86, so here's my measure of angle S would be right in there. And then they want to know what would be the measure of angle R. Now we don't even really need the picture for this because based on how my parallelogram is named, I know that R and S are consecutive angles, which means that they must be supplementary. So if S measures 86, we know that R must be its supplement and measure 94 degrees. Pause the video and try to quickly solve 1 and 2. I want to challenge you to not use a calculator. This is math that should be mental math for you at this point. So we have consecutive angles and the pair must be supplementary. So the supplement of 53 degrees we know is 127 degrees. And then for x over here, it has to have a supplement with 113. So what would add us up to 180? That would be 67. Theorem 42 is just showing you that our opposite angles are congruent, like I've already discussed. Theorem 43 is talking about our diagonals. Each diagonal in a parallelogram bisects each other. Now that does not mean that they have any relationship with each other aside from that, but what that does tell me, if there's a point E here dead in the center, then from BE to ED will be congruent. And from EAE and EC will also be congruent. So that point where my diagonals meet is a bisector for both of them. Try to solve through your got it. You really only need 4 steps for this proof. We start by saying that AK is congruent to MK, AK congruent to MK, and that ABCD right here is a parallelogram. So go ahead and try this proof to prove that BCD is congruent to CMD. So I've got everything color-coded here for us to work through our solution. So starting with our parallelogram and our congruent sides as our given, we always want to restate our given facts that are useful. So then I see that angle A will be congruent to angle BCD because in a parallelogram, my opposite angles are congruent. Then from there, I move on and say that angle A is congruent to angle CMD, which is this angle right in here, because I really have an isosceles triangle. When I have 2 congruent legs of a triangle, I know that the base angles will be congruent because that forms an isosceles triangle. And then I can just say that BCD is congruent to CMD by the transitive property. They were both equal to angle A, so therefore I can just relate them to each other. So for number 3 here, we're trying to prove that AC and BD bisect each other. We're trying to prove Theorem 43. So pause the video, see if you can fill in all of our blanks here to really write out the proof for Theorem 43. Alright, so the first thing we do is state our given, knowing that it's a parallelogram. Then I relate AB being parallel to DC because it's the definition of a parallelogram. We know opposite sides are going to be parallel. Then angles 1 and 4 are congruent, and angles 2 and 3 are congruent because we know these lines are parallel, and those angles now are alternate interior angles. So because we have alternate interior angles, I can prove congruency. And then I see that AB is congruent to DC. Well, that's just dealing with their lengths. And again, opposite sides of a parallelogram are congruent, so that really goes back to the definition of the parallelogram. Now I want to say, what is our statement for D? That angle side angle tells me, well, angle side angle relates triangle congruence. So we are relating triangle ABE and CDE being congruent. From there, we can relate AE and CE congruent, as well as BE and DE congruent, because corresponding parts of congruent triangles are congruent, or there you could write CPCTC. And our last statement that we make based on the definition of a bisector is that my lines AC and BD bisect each other at E because we know that they have created congruent parts, and that is exactly what a bisector does. Please make sure you've worked through problem 3 to get to this point. We want to find the measures of PR and SQ here. So those are the lengths of my diagonals. Now we're going to have to use a little bit of what we know, such as my diagonals bisect each other. So that's going to be the important thing to know here. Pause the video, try to work your way through this problem. Come back if you need help or to verify your answer. So what we see here is, because I have the diagonals of a parallelogram, is that they bisect each other. So each individual segment here will be equal. So 3y minus 7 is equal to 2x, and then y would be equal to x plus 1. This statement right here is very important because then I can plug in and substitute for the y and be able to only have x's in this equation, which will then let me solve for x, and I can plug it back in and solve for y. So if you have yet to do it, pause the video and work your solution. Alright, so let's look at how we approach this. We take our equation right here and replace in the x plus 1 for the y. I then distribute my 3 into both the x and the 1, so I get 3x plus 3, still have that minus 7 equal to 2x. I combine my like terms, so I have 3x minus 4 now equal to 2x. Now, this is where the process, you can choose whichever method you like. I like to make everything positive. So I want to bring my 4 over here to make it positive, and then if I subtract 2x, I'll still have a positive x value. So I first add 4 to both sides, then I subtract my 2x, which gives me that the x value is 4. Now that I have the x value, I can plug it into this equation for the y value and say y is going to be x plus 1. So I substitute in the 4 and find out that y is actually 5. Once I know that, remember, we're not trying to solve for x and y, we're trying to solve for PR and SQ. So to solve for PR, I'm going to start by saying PR is actually the combined segments of PT and TR. PT was this expression 3y minus 7, but instead I substitute in for the y and sub in that 5. I do the math and find out that PR is equal to 16. I do the same thing for SQ, but it is the combined segments of ST and TQ. So then ST, I plug in my 4 for the X plus 1, and then my Y is 5. I combine them and find out that SQ is 10. Now to answer part B, it says in problem 3, really it could mean in the got it even, because they were both dealing with the same process, but it says, does it matter which variable we solve for first? No, it really doesn't. But the issue would be here, if I try to solve for the variable x first, I would do that by dividing by 2. Dividing 3 by 2 is not very fun, and dividing by 7 by 2 is also not very fun. So that's how we decide what variable to solve for first, is what math is easier to deal with. For 4 and 5, you want to go ahead and try to solve those. I'm running out of time, so when you come back, I'm not going to show you the solution process, I'm just going to show you the answers. And there are your solved values for x and y on both 4 and 5. Tried to color code Theorem 44 here to make it a little bit simpler to understand, but what it says is that if we have 3 or more parallel lines, that then we have one transversal that cuts it and has congruent sections, so here we see our 2 congruent parts, then any transversal that will cut through these parallel segments will also create congruent sections. So in our got it here, hopefully you've worked through the Pearson module to make it here, EF, FG, and GH are all shown to be congruent and equal to 6. I'm then told the entire span of AD is 15, which means that each of these also must be congruent. So CD would then be 5. So go ahead and pause the video for 6 and 7. Try to figure out the lengths of ZU and WV. Because we're told that my transversal from P to S all has congruent segments here, I know that any transversal through these parallels will have congruent segments. So ZU, this segment up here, will be congruent to ZX, which is congruent to XT. Therefore, ZU is 3. And for WV, I see that that's the entire transversal here. So we have 3 congruent segments, and when I add those all up, it's 6.75. These are the last problems that we're going to have a chance to do, so please pause the video and try to solve these. I'm not going to have much time, so when you come back, I'm going to quickly talk through all the solutions for this, and that will be the end of our lesson. All right, we're going to fly through 8, 9, 10, and 11 first, then we'll pause and do number 12. So for 8, what we see is we're trying to solve for the measure of angle A, and A is consecutive with B, so we know they must be a supplementary pair, so A ends up being 53 degrees. What we see about measure of angle D is that D is opposite our angle B, and since this is a parallelogram, we know that they must be congruent, so we know that D is 127 degrees. For number 10, trying to find x, we know that opposite sides are equal, so I set up an equation to make them equal. In the same step, just to save room, I added 3 to both sides and subtracted x from both sides and got that x is equal to 5. And then I solved 11 using that if x is equal to 5, AB must then be equal to 7. Key thing to pay attention to in 12 is I have 3 parallel lines cut by a transversal CA that shows me that I have congruent segments made by the parallel lines, which tells me any transversal that cuts through these parallel will have congruent segments. So when I look to find ED, ED is this little unknown segment there, which must be congruent to the continuation of that transversal. So that segment being 12 tells me that ED is going to be 12. And then when I look for FD, FD is the entire transversal, or the entire both segments through my parallel line, so I just have 2 12s, and I get that it is 24. That is everything I have for today's lesson, so please make sure that all of it made sense. Let me know if anything was confusing or if you need any more help for anything. Please make sure you try your practice work, and I will see you guys in class. Have a terrific day.